Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. Okay, we intend to start with a new topic within partial derivatives. This is partial derivatives in economics. So in this lecture, we are going to study where we use the concept of partial derivatives, particularly in economics. Okay, all of you can recall that in the previous few lectures we have been discussing partial derivatives in two variables. Okay, we have also done the higher order partial derivatives. Now let us see in this lecture where we can apply this particular concept in economics. So first of all, let's look at the first application, application 1. This is the very famous production function in microeconomics. Okay, so consider an agricultural production function. Consider an agricultural production function which is given to us as output is a function of capital, labor, okay, and land. Again, the example which I have taken is exactly from the book Sater and Hammond. The example or the application is exactly taken from the book Sater and Hammond, the 4th edition. Okay, so I can quickly write for more clarity. Y denotes the number of units produced. Y denotes the number of units produced. K denotes capital invested. L denotes the labor input. And T denotes the area of the agricultural land used. So basically, we have output as a function of 3 inputs: capital, labor, and area of agricultural land used. K, L, and T. So now, if I do the first order partial derivatives of this function, what are we going to get? So we can now write economic interpretations. Economic interpretations of first order partial derivatives. Economic interpretations of the first order partial derivatives. So we are going to have the following interpretations. Okay, if I partially differentiate my output with respect to capital, which I can also call as fk dash, what will that be? How will I interpret this? So this is the marginal product of capital. This is the marginal product of capital. That is the rate of change of output. The rate of change of output with respect to capital when labor and land, L and T, are kept constant, or I can say they are held fixed. So del y by del k, which is fk dash, is going to give me the marginal product of capital, which is the rate of change of output with respect to capital, keeping the other two units, labor and land, constant. Similarly, if I write the second interpretation, if I erase this interpretation off, and if I write the second interpretation, what will del y by del L be? I can write it as FL dash. It is the marginal product of labor. That is the rate of change of output with respect to labor when capital and land are held fixed. And similarly, I can do the next interpretation, which is going to be my third interpretation. What will del y by del t be? I can write it as ft dash. This is going to be the marginal product of land, agricultural land. That is the rate of change of output with respect to the area of the agricultural land T when capital and labor are held fixed. So these are going to be the interpretations of the first order partial derivatives. Okay, so if I take an example of application 1, so consider this example. Suppose my production function is as follows. F as a function of k, l and t is given to us as a k to the power a, l to the power b, t to the power c. Okay, where you can see that capital A, small a, b and c are all positive constants. Clearly, this production function is a Cobb-Douglas type production function. It's a Cobb-Douglas production function. I can quickly find out all the first order partial derivatives. The first order partial derivatives of the above function are fk dash, which is nothing but if I partially differentiate this function with respect to k, capital A, small a, k to the power a minus 1, l to the power b, t to the power c. You can see that it's all positive because capital A, small a, b and c are all positive constants. And all the inputs k, l and t are anyways positive. If I find out marginal productivity of output with respect to labor, keeping k and t constant, it's a, b, k to the power a. Okay, it's a, b, k to the power a, l to the power b minus 1, t to the power c, which is again positive. And if we find out ft dash, which is the marginal productivity of agricultural land, keeping capital and labor constant, it is a, c, k to the power a, l to the power b, t to the power c minus 1, which is again positive. So clearly you can see that all the marginal productivities are positive. All the marginal productivities are positive. What does this mean? This means that every additional increase in capital, keeping L and T constant, or every additional increase in labor, keeping K and T constant, or every additional increase in T, keeping K and L constant, is going to increase the output. Okay, so we can write thus an increase in capital or labor or land will increase the number of units produced. But remember, when you are increasing one factor, others are kept constant. When you are increasing capital, labor and land are constant. When you are increasing labor, capital and land are constant. When you are increasing land, capital and labor are constant. Okay, so that is my output increases. And now we can also work out the second order partial derivatives. So if I erase this off and if I work out the second order partial derivatives, let's see what do we get and let's see how do we interpret the second order partial derivatives. Okay, so let's now look at the second order partial derivatives. So I can write the second order partial derivatives of the above function are, if I calculate the direct derivatives, fkk double dash will be a minus 1, k to the power a minus 2, l to the power b, t to the power c. Remember, fkk double dash you get by differentiating fk dash again with respect to k. Similarly, FLL double dash will come out as a b b minus 1, k to the power a, l to the power b minus 2, t to the power c. And FTT double dash is going to be a c c minus 1, k to the power a, l to the power b, t to the power c minus. Now, assuming that a, b, and c are all less than 1. Suppose they lie between 0 and 1. In this case, all these will be less than 0. So I can write fkk dash will be less than 0, FLL dash will be less than 0, FTT double dash will be less than 0. What does this mean? This simply means that marginal productivities are increasing but at a diminishing rate. So this means, you can clearly see, guys, if A, B, and C lie between 0 and 1, this is positive, this is positive, this is positive, these are all positive. But since A, B, and C lie between 0 and 1, this is negative. And any negative term multiplied by all positive terms is going to cause the whole term to become negative. So if A, B, and C particularly lie between 0 and 1, that means they are fractions or proportions. Then this means that marginal productivities are increasing, but at a diminishing rate. They are increasing, but at a diminishing rate. This means that when you are adding more capital, keeping labor and land constant, or when you are adding more labor, keeping capital and land constant, or when you are adding more land, keeping capital and labor constant, your output is rising. But your output is rising at a decreasing rate. Rising at a decreasing rate means concave. If you draw the picture, it's going to be a concave production function. But again, we cannot draw the picture because it's going to be a three-dimensional figure. Not 3 dimension, it's actually going to be a 4 dimension. If I draw the graph of this function, the graph of this function is going to be in the 4D space. Its level curve is going to be in the 3D space. Its graph is going to be in the 4D space, because you will have 4 axes: capital, labor, land, and the function itself. So we cannot draw the graph, but you need to understand that the marginal productivities are rising, but they are rising at a diminishing rate. That means increase in any of these inputs causes the output to rise, but output is rising slowly. Okay, so let's look at a practice question. So I hope all students have understood till here and have no doubts. Okay, now let's look at a practice question based on this particular concept. Let's look at this practice question. I have taken up this question from Sitsaton and Hammond only for reference. So consider the modified version. Consider the modified version of the Cobb-Douglas function. Consider the modified version of the Cobb-Douglas function as f as a function of capital and labor, which is a k to the power a, l to the power b, e to the power ck divided by l. In this case, you can see that my output is only a function of two inputs, capital and labor. Again, capital A, small a, B, and C are all positive constants. The question asks us compute Fk dash and Fl dash and discuss their signs. Okay, so let's solve this question. Let's quickly compute the first order partial derivatives with respect to capital and labor. So our Fk dash will be del f by del k. If I partially differentiate this function with respect to k, what do I get? Capital A, small a, k to the power a minus 1, L to the power b times. Okay, we will have to use the product rule here, guys, because we have k coming up 2 times. You can see k is here also and k is here also. So it's going to be a, L, b. I applied the product rule in this term and this term. So k to the power a times e to the power ck by l times ck by l ka derivative with respect to k will be c by l plus e to the power ck by l times k to the power a ka derivative with respect to k is a k a minus. Okay, so this is what I get. I can further solve it to make it look more sophisticated. It looks like a l b. Okay, and then I can write it as c k to the power a e to the power ck by l divided by l plus a k to the power a minus 1 e to the power ck by l. Now we can take things common from this expression and this expression. I can take k to the power a common and I can take e to the power ck by l common. So I am left with c by l plus I am left with a, and I have taken k to the power a common. So this is k to the power a minus 1. That means a by k. This is what I get inside when I take things common. Okay. And now what is this term, guys? This term is what? It is nothing but my production function itself. This is nothing but f of kl. So what can I write? I can write that my fk dash is f as a function of k and l times c by l plus a by k. It is c by l plus a by k. This is my fk dash. Okay. Now we are in a position to quickly calculate fl dash as well, and then we can interpret both of them. So I am erasing fk dash now, and let us calculate fl dash. Okay, erasing fk dash, let's quickly calculate fl dash. So our fl dash, which is the second first order partial derivative, will be del f by del l, which is going to be a k to the power a. Now we are going to apply product rule in 2 terms, l to the power b and e to the power ck by l. So it's going to be L to the power B into E to the power CK by L times minus CK by L square when I differentiate CK by L partially with respect to L, plus the product rule E to the power CK by L times L to the power B ka derivative B L to the power B minus 1. B L to the power B minus 1. Let me write it more clearly. B L to the power B minus. So our FL dash becomes, let's again solve this, a k to the power a times, now this I can write as L to the power B times e to the power ck by L times minus ck by L square plus L to the power B minus 1 times B times e to the power ck by L. Now again, let's take things common. So I can take A, k to the power A, L to the power B, e to the power ck by L common. So this and this are common. So I get minus ck by L square plus B, we are left with B, and L to the power B minus 1. I have taken L to the power B common, so divided by L. So if I write, what is my FL dash finally coming out? So if I erase the initial part of the differentiation, I can write my FL dash in final terms. What is this? This is nothing but f of KL, my production function. So this is f of KL times B by L minus CK by L square. This is my FL dash, and I'm just writing FK dash again. Our FK dash is f of KL times C by L plus A by L. So these are the values of FL dash and FK dash which I get from this particular production function. These are my marginal productivities with respect to labor and capital. Okay, so now let us discuss their signs. So let's first talk about FK dash. So K and L are anyways positive. If K and L are positive, you will observe that FK dash is anyways positive, because we know that output is always positive. We are given that capital A, small a, B and C are all positive. So these are all positive. If my capital and labor are also positive, my FK dash is anyways positive. But look at FL dash. If you look at FL dash, FKL is positive. Individually, L is also positive. B and C are also positive. But I can say for FL dash to be positive, B by L should be greater than CK by L square. So L cancels with the power. So what do we get? This implies B should be greater than CK by L. So this is the condition we get for FL dash to be positive. Remember, FK dash will anyways be positive because all the constants are positive, capital and labor are inputs which are always positive. But for FL dash to be positive, that means for marginal productivity of labor to be positive, B should be greater than CK by L. That means this term should be greater than this term for FL dash to be positive. So I hope all students have understood this question and have no doubts. Okay, let's now look at the next particular practice question, question 2. For the general Cobb-Douglas production function, given in the logarithmic form. Okay, we are given the Cobb-Douglas function in the natural logarithmic form as ln f is equal to ln a plus a1 ln x1 plus a2 ln x2 plus dot 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 a n ln xn. This is nothing but the logarithmic form of the Cobb-Douglas production function in general. What is my Cobb-Douglas production function in general? F is equal to a x1 to the power a1, x2 to the power a2 multiplied n times xn to the power an. This is my general Cobb-Douglas production function. If I take natural logs on both sides, this is what I get. The question asks us show that summation as I goes on from 1 to n, xi times del f by del xi equals a1 plus a2 plus dot 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 an times f. Again, this is a question which uses the concept of partial differentiation. Okay, so let's solve this question. So consider the logarithmic form given to us. Ln f is equal to ln a plus a1 ln x1 plus a2 ln x2 plus dot 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 an ln xn. So differentiating the above equation partially with respect to xi, what do I get? If I differentiate this equation partially with respect to xi, where xi can be any of the x's, it is going to be 1 upon f times del f by del xi equals ai times ln xi ka derivative will be 1 upon xi. You can think of ln xi as somewhere in the between. So I can write it like this: plus ai ln xi plus dot 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 we can have an ln xn. So ai ln xi is somewhere, is any term, general term. So if I differentiate it, this is what I get. Partially if I differentiate with respect to xi. Now we need to figure out this term. That means I need to multiply both sides by xi. Multiplying both sides by xi. What do I get if I multiply both sides by xi of this term? Xi by f times del f by del xi is equal to xi times a by xi. Xi cancel out on the right. So now I've got this term. Okay, so I need this term. So if I take f on the right hand side, so I can write xi times del f by del xi is equal to ai times f, where f is my Cobb-Douglas production function in general. Now all I have to do is sum up. So if I sum up, therefore summation as I goes on from 1 to n xi times del f by del xi will be summation as I goes on from 1 to n ai times f. Now guys, f is a constant, it comes out, times summation as I goes on from 1 to n ai. And what is summation ai? A1 plus A2 plus dot 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 an, which is nothing but my right hand side. So we have shown that summation xi times del f by del xi is equal to a1 plus a2 plus dot 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 an times the function f. So again, the objective was that students should learn how to partially differentiate the function and apply this form to get the required answer on the right hand side. Okay, so I hope all students have understood this and have no doubts. Okay, now let's look at the last application for this lecture. Now application 1 was based on production. Application 2 is based on consumption. So the function u, which is a function of x1 x2 dot 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 xn, represents, or I can say if the function u as a function of x1 to xn represents the utility function of an individual, of an individual from consuming respective quantities x1, x2, xn of n different goods, then define del u by del xi as the marginal utility of the ith good. So in application 1, when you differentiate the production function with respect to the ith unit, you get the marginal product of the ith unit. In application 2, the same thing holds true from consumer theory point of view. If you differentiate the utility function of an individual with respect to the ith good, you get the marginal utility of the ith good. Okay, so let's take an example. Suppose my utility function, suppose my u as a function of x1 to xn is a1 ln times x1 minus c1 plus a2 ln times x2 minus c2 plus dot dot dot. I can stretch it to an times ln of xn minus cn. Then we can calculate all the marginal utilities. Del u by del x1 will be a1 upon x1 minus c1. Del u by del x2 will be a2 upon x2 minus c2. And I can stretch it on and I can write del u by del xn will be an divided by xn minus cn. Clearly, you can see that if a1 to an all are positive and all the xi's are greater than the corresponding ci's for all I going on from 1 to n. If xi's are greater than ci's, that means all these denominators are positive. All these denominators are positive. If all the denominators are positive and all the numerators are also positive, then this implies all the marginal utilities are positive for this particular function. All the marginal utilities are positive. So basically, application 2 was just a replica of application 1. Application 1 is based on production theory. Application 2 is based on consumer theory. When you partially differentiate the production function with respect to the ith unit, you get the marginal product, keeping all other inputs constant. When you partially differentiate the utility function of the consumer with respect to the ith good, you get the marginal utility of that good, keeping all other goods constant. Okay, so this is where I intend to stop in this particular lecture. The objective of this lecture was to discuss with students the applications of partial derivatives in the field of economics. So in the next lecture, we will be solving some problems from the Sater and Hammond book based on economic applications of partial derivatives. So I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.